Hi, my name is Jorge. I'm here to talk about quantifying interpretability of models trained on CoinRun. Now, for anyone else who might be new to interpretability, I just want to clarify that phrase. As Alethea Power said yesterday in their presentation, interpretability is essentially the field of mind reading for neural networks. Unlike with humans, when a human makes a decision, such as when you're seeing an image and you want to classify what exactly that image looks like, and a human says, "Oh, this image of a dog is of a dog," you can ask the human why they think it's a dog. Whereas sorry, technical thing. Okay. Whereas with the computer neural networks, when we use them, you can't ask a neural network exactly why do you think an image is classified this way. Instead, we use interpretability as a means of breaking down neural networks, understanding why they make the choices they do. So that is interpretability, to be clear. And also, I want to introduce myself before I get into the details of this, that I'm a software engineer. I joined the scholarship program back in February. Under my mentor, Carl Cobb, I learned reinforcement learning for 2 months, after which I worked on this project. And it's a pleasure to be here today. So let's get started on it. All right, so the whole goal of my project is testing the diversity hypothesis. Now, the diversity hypothesis, as proposed in the original paper, which is currently unpublished, but written by Jacob Hilton and Chris Olah, two engineers and researchers here at OpenAI. And by the way, if you have access to this, to their draft, I highly recommend checking it out. The diversity hypothesis is as follows. Interpretable features tend to arise at a given level of abstraction if and only if the training distribution is diverse enough at that level of abstraction. So let's clarify a few terms here. One, that diversity in this context is, in our use, going to be just the amount of distinct input that a neural network gets to train on. So for example, with an image classifier, if you give a neural network 100 examples of images to train on and understand how to classify, that would be less diverse than a network that's been given 100,000 images to train on and understand and classify. And when we speak of levels of abstraction here, we're mostly speaking about different layers of our neural network. Essentially, neural networks are divided into layers. That early layers tend to catch simple patterns like lines and shapes, and later layers tend to catch more complex and abstract patterns like dogs or cats. This is, again, in the context of just image classification. So essentially, as a model trains on more diverse data, we expect that it's easier for us to understand why a model makes the choices it does. And do we have any proof of this? Yeah, we do, because this unpublished paper made an experiment, specifically in the context of CoinRun, which I'll go into detail later, but for now, pictured it as a game similar to Mario Brothers, where essentially have an agent that is controlling a little character that goes around the level. Now, as you can see in this left slide, that as models, this lower bar shows models and the specific architecture and a differing amount of levels that it's been trained on. So on the left side represents models that have been trained on very little data, about 100 distinct training levels, whereas the right side shows models that the same model trained on more training data. We can see that, as expected, it performs well when tested against data it hasn't seen, if it's been trained on a larger amount of data. So essentially, as you train on more data, you expect the models to perform better in testing. And just as the performance improves, so does the interpretability of the features of this model, essentially meaning that models that have been trained on very little data, in CoinRun in this instance, only have about 1 in every 5 features that is even like understandable to humans. As in, if a human breaks down the network, they can only understand roughly 1 in every 5 features or individual components of the network and what they're doing. Whereas as a model is trained on more and more training levels, the amount of features that are interpretable to humans goes up to 4 out of 5. And now essentially my goal here is to test out and so this, of course, indicates that the diversity hypothesis is valid. And my goal is to test out the same. The only difference is that the researchers who generated this graph did so with a human in the loop. Now, this process takes a while. It takes roughly an hour and a half for every individual researcher to go and look at what these models are going through and matching the features with their results and trying to understand what they're looking at. And it's a long process. I'd like to make a definition for interpretability that's algorithmic, that a computer can use, so that we don't have to have a human in the loop to test this idea of interpretability. This will help us scale up experimenting. So let's first start off by breaking down the tools used in this previous experiment. And the two in particular will be coin run and attribution. So coin run, the domain that this training is done on, is Mario platformer, as mentioned before, and I'm going to show an example of it. So here we see a player jumping through a platform, avoiding a little enemy, like that buzzsaw right there, and grabbing the gold coin at the end. Now, the player jumps through, avoids enemies, and if it lands on an enemy, it fails the level and doesn't get a reward. If it gets a gold coin, it actually is successful in completing the level. Now, I want to emphasize that with coin run, essentially there's different assets and textures, or different textures for the assets, that as you go through levels, there's more diversity than just like placement of platforms. There's also what the platforms look like, what the background looks like, what the player looks like. So there's a lot of potential diversity in how the assets are recognized and how a network can understand the domain. Now let's go to attribution. So how do we know what a network is looking at or what it's paying attention to? This is what attribution allows us to see. So from a technical point of view, attribution is when the output of a network, when we get the output of a network and we get its derivative with respect to the input to a network. Essentially, we can abstract this away as it allows us to see what a network is most paying attention to when it's classifying or doing some action with an input. So let's imagine in the domain of classifying images, what that looks like. So in this first image, we have a picture of a bird. If we had an image classifier that ran this image, we would expect the classifier to output bird as a classification. In the second frame, we run attribution on that network with respect to this image, and it tells us, and it gives us an output with the same exact dimensions as the image, showing that the whiter pixels here, the pixels with the higher values, are the ones that the network is most paying attention to. So in this case, we can see that the network is paying attention to the eye of the bird, the beak of the bird, the feathers along the bird's head, and even the plumage like closer to the base. And that's really interesting. It doesn't pay attention to the grass at all. And we can see that if you map the most noticeable pixels to the original image, you get this kind of results in image of just the bird. That essentially the grass is not weighing in on a network's decision to classify this image as a bird. So this allows us to see what that network's paying attention to. Can we use this on coin run? And we can. I'm going to show an example. Essentially, we're doing a very similar process, except when a model is being trained and running on coin run, it's specifically outputting two things: the controls of the player, because that's how it controls the player when it's playing, and something called the value function, which is really just an estimate of the model's performance. That it'll have a high value if the model thinks it's doing well, and low if not. So with this results of attribution, let's see what the model is looking at in a very specific track of coin run. So we'll see here, as the player jumps through the game, you can actually see that the model's paying attention to buzzsaws in the game, as in like it's actually seeing, oh, there's like an enemy, I have to avoid it. And it's really easy as for a human to see, okay, this is exactly what the model is looking at. Now, I want to clarify that in this context, we're not running attribution on the entire network, but on a section. This allows us to see only what the model thinks of in terms of abstract ideas and more like developed assets and where they are in the image. And it also allows us to have multiple results, which is why you see these multiple colors, that there's multiple features that a network can use to interpret the image. Now, let's see what a poor interpretable example would be. Essentially, a player runs through, and as it jumps, you can see there's these little purple kind of shapes in the background. That's a feature that is picking up random artifacts in the background. It has no idea what is like relevant to itself and what's not. Whereas the other model, we could tell easily. Here, a human wouldn't be able to tell you what's this model paying attention to. We have no idea. It's just like these random shapes in the background. There's some aspects of it that maybe you can guess what the model is looking at, but ultimately I would classify this feature as uninterpretable. So with this process, this is a human-in-the-loop process I just described. Can we make this into something a human could do for us instead? And we can, or at least we can try. So this is kind of my little trying to add something new here. I'm going to define interpretability for this context of coin run as just the area of a quantity equivalent to the area of intersection between attribution and the objects of interest divided by the output of attribution. So that's kind of a mouthful, but let's kind of break down what that looks like. Essentially, as a character jumps through the game, we have this one example of a frame. We can actually separate what I call the objects of interest, which are really just any objects that aren't the background, and give them, put them in an image where everything has a value of 1 except for the background. So that's what this looks like. Essentially, everything is white except for the background, which is black. And with this, what we call a mask of assets, we can add the attribution results. And let's say here we have these two little spots from attribution, roughly 10 pixels each. And we see that 10 pixels are right on top of a wall, so it intersects with the object of interest, and 10 are not, they're in the background. So again, with our quantity of interpretability, we see that the numerator, essentially the intersection, is 10 pixels divided by the total area of attribution, which is 10 plus 10, 20 pixels. So 10 divided by 20, that's a 50% interpretability score for this specific frame. Now, if we do this process, not just for one frame, but for 512, and we do it not just for one feature, but for all features of a neural network, and we get the average of all those results, we can have what I claim to be an interpretability score for the model. Now, what does that look like? Well, it looks the same for all the models I trained on, going from models trained on 100 levels, which in this context is very small, and models trained on 100,000 levels, which is a model that is trained on a lot of data, and we would expect to have very interpretable features if the hypothesis were valid. Now, what does this show? Because I've myself gone through this human-in-the-loop domain experiment, and I trust that these human-in-the-loop results are valid and do reflect true interpretability, this means that my definition for interpretability currently isn't working out. They're all roughly at 35 to 40%. Why is that? Well, it's very heavily because a lot of my results of attribution are not as small as I've shown you in this example, where often the examples, the results of attribution are actually much larger, or on the order magnitude of like 20 by 20 pixels. And they take up a lot of the screen. And especially when you have a lot of assets that take up the majority of screen, it ends up picking up about the same amount of the mask every time. And it's not a good method. Now, I can narrow down the scope because this is partially due to a method that's just called using the receptive field, where you're essentially trying to translate the results of attribution to the input domain. And it's currently not essentially, it's not working quite well because you kind of have to use the receptive field in a way in which you're weighing the more connected parts of a network with the lesser connected parts of the network. And so essentially some refinement and obvious improvements can be done, but currently the measurement does not work. So what are my conclusions here? I think that this ability, because interpretability is still like something that can be calculated with an algorithmic process with a human in the loop, I think it can be done by a computer. But we still have to refine this current definition I have. And this is just in the domain of coin run. It has to be expanded to other domains to be functional for us. And what else? So thus, my experiment doesn't actually prove or disprove the diversity hypothesis, but I still think that it's important to try to further experiment and see if this hypothesis is valid, because the hypothesis is very powerful, that if we understand that diversity of features does increase with generalization of a model, this is a new axis by which we can improve models, and it's very exciting. But so yes, so that's my conclusions. I'd like to acknowledge very quickly because I'm a little short on time, just my mentor, Carl Cobb, who's fantastic during this program. And honestly, this work wouldn't have been possible, or I wouldn't have been able to do this work without him. Jacob Hilton and Chris Ola, the original writers of the paper, who did a fantastic job, and I highly recommend looking at it if you have access, because it's not yet published. Muraya and Cristina, who ran the Scholars Program and have done a great job doing it, and were very supportive. Mario and Francis for making this presentation possible. Alethea, Andre, Kathy, Kamal, Gata, Pamela, the other scholars, and they were fantastic. Greg and Brockman and Altman for essentially making everything here possible. And Rachel Yang, my fiance, who was also great support during this work. Thank you very much. I will check now if there are any questions. How can you tell if a distribution is diverse? Excellent question. Is there a metric to quantify the diversity property of a distribution of a model? Great question. So in this case, and I want of a distribution or model. So in this case, we're thinking of diversity in the context of the input distribution. And I'm sure there's better ways to do this in other domains, but in the coin run domain, I'm only defining diversity as the amount of distinct levels that an agent is trained on. So it's really just kind of trusting, it's not trying to, this current definition of diversity isn't trying to distinguish between how diverse two different levels are, more just kind of going with the easy first solution of any distinct model is, like the amount of distinct levels that a model is trained on is the level of diversity it has. Thank you for that question, by the way. Since you are using a dynamic image video, how is the attribution model able to perform consistent identification and tracking of the objects it is attending to? Let me swallow that or digest that real quick. Since you are, how is the attribution able to perform consistent identification and tracking of the objects it is attending to? It's a great question. So ultimately, the model is operating on the frame by frame basis. There's no consistent, like, oh, this is what I used for attribution last time, this is what I'm using this time. So there is a lot of flickering where it's not that consistent. But I think with the examples I showed, there was one that was super interpretable, and it shows just how well it's actually generalizing and is human interpretable, that it's actually able to consistently recognize features from one frame to the next. It's not that, like, it's sort of, that shows how well that it's generalized, that even in a dynamic image or in a video, that it's still able to like consistently make sense to humans, that you don't have to go frame by frame. So great question. I would say for the less interpretable ones, it doesn't look consistent at all. I had to pause, if you remember the less interpretable model, I had to pause it multiple times just for you to see the purple haze and see what it's picking up. So yeah, I hope that answers your question. You can ask another if it did not. How is attribution different from saliency maps? Excellent question. Attribution is saliency maps. The term attribution, I don't know why it picked up in specific fields relative to others, but I want to show real quick and give thanks to, here we go, K. Vilaldi, Zimmerman. All right, this paper I'm referencing here, Deep Inside Convolutional Networks, coined the term saliency maps. I believe they did this before the term attribution caught on. I don't know why there's a different usage in the field. And also, if anyone knows why, or if there is like a difference in context, I would love to know. But yeah, so essentially they're the same thing. How would you think the interpretability of the model, as you define it, would scale to other games besides Coin Run, like Bouncy Bob? Excellent question. My original goal, or my stretch goal when I started was to actually try an experiment, should I successfully define interpretability for the context of Coin Run on another ProcGen game. I have to admit, in the heat of the moment of the presentation, I don't remember which game Bouncy Bob is. So there's a few things to keep in mind here. One, that Coin Run is a game in which the assets of value take up about like 50% or less of the screen at a time. If you're playing a game like checkers, the assets of value are taking up the entire screen. So it doesn't actually change very well to that kind of game. So Bouncy Bob, if it's a game where assets are relatively rare, or not rare, but at least less than 50% of the screen, I think it could work. There's a few other nuances on like what else would the interpretability definition work for. But yeah, I hope that answers your question. Also make sure to check out Bouncy Bob later. Ooh, another one. Why does good attribution saliency imply interpretability? Isn't this mostly an accidental correlation? Great question. Though useful and not a causal implication. Let me also digest this one real quick. Imply interpretability. Okay, so essentially what the purpose of testing the diversity hypothesis is testing if this is true. If good attribution saliency kind of does imply interpretability. Is that right? No, not exactly. It's okay. So I'm going to say that good attribution saliency is in itself like not really a phrase. What makes it good? Here we're using it. It's just the tool itself, attribution. That we're just saying that if attribution aligns with what we consider to be an object of importance in a game, then it is good. And so it's sort of, it's not an, so it's sort of like, it's kind of coming back to this idea of like, what does it mean to be human interpretable? Where for us, and for this, the context of this experiment, it's saying that we humans pay attention to things. And like when you look with your eye, that you tend to focus on specific objects and narrow down your domain in order to like digest an image or kind of interpret it. And so in the same way, we're sort of expecting like, okay, there has to be certain parts of the image that the network is most sensitive to make a prop for us to actually understand that it's using those parts of the image to interpret. I'm not satisfied with this answer. Reach out to me. I'd love to talk about this more. And I also think that Jacob Hilton would have a much better response to this than myself, because he wrote a lot of this original work, and Chris Olah in the paper. But yeah, but thank you for the question. Is there another one down? I don't think so. And I think Mudaya is grabbing the screen. So thank you very much, y'all.